Hello everyone. This is in continuation with our series of videos on graph theory. This is our third video, different forms of graphs. What are the different forms of graphs will be seen in this particular session. First one, simple graph. A graph is called simple graph if the graph is undirected and does not contain any self loops or multiple edges. For example, if you look into it, do not have any self loop like this or like this, and then multiple edges are not there, means there is AC, there is no one more edge here or one more edge here or one more edge here. That is called a simple graph. Multi-graph, a graph having no self loops, there are no self loops here, but having parallel edge or edges in it is called a multi-graph. Here you may note there are two ways, this way and this way also. So it is having parallel edges. These two are parallel to each other. So that we call it as multi-graph. Then pseudograph, a graph having no parallel edges like this, but having self loop. Here it is. There is a self loop here. It is called a pseudograph. Then null graph, a graph whose edge set is empty is called as null graph. There are no edges here, only vertices are there. There are no edges here. This we call it as a null graph. Means a null graph does not contain any edges in it. Next one, trivial graph. A graph having only one vertex like this in it is called a trivial graph. This is the smallest possible graph. Trivial graph is the smallest possible graph. Next, subgraph, a graph whose vertices and edges are subset of another graph is called a subgraph. This is the main graph. This is the subgraph. We call this main graph as graph A, subgraph as graph A dash. In this, we may notice that A, B, C, D, there are four vertices and 1, 2, 3, 4, 5, 6, 7 edges are there. Whereas here we may notice three vertices are there, means those vertices are the same what is here A, B, D. And we may notice that the vertex set of this graph is a subset of vertex set of this graph. Similarly, the edge set of this subgraph is a subset of the edge set of this graph. So that is a condition here. A subgraph of a graph G, that is this graph, is equal to V comma E is a graph G dash, V dash comma E dash, such that V dash, that means the vertex set of the subgraph is a subset of the vertex set of the original graph. Similarly, the edge set of this graph, which is E dash, is a subset of the edge set of this particular graph. So further, this E dash should be a subset of the cross product of the vertices V dash set and V dash set. So if we take a cross product of V dash cross V dash, E dash will be definitely a subset of that only. A complete graph. A simple graph G is said to be complete if every vertex in G is connected with every other vertex. We may notice every vertex is connected. 1 and 2 are connected. 1, 2 are connected. 1, 3 are connected. 2, 3 are connected. Everything is getting connected. The complete graph with the n vertices is denoted by k suffix n and has nc2 undirected edges, or we can say n into n minus 1 by 2 undirected edges. So this is a complete graph having two vertices. Here, this is a complete graph having three vertices. This is a complete graph having four vertices. This is a complete graph having five vertices. We may note the number of number of edges in this. Since it is having two vertex, it will have 2 into 2 minus 1 by 2, which is nothing but one edge only. Here it is 3C2, it should be. 3C2 is nothing but 3. So we have 3 edges, 1, 2, 3. Here it is 4C2. 4C2 means it is 4 into 3 by 2, which is nothing but 6 edges. We have 6 edges, 1, 2, 3, 4, 5, and 6. Here it is 5C2. 5C2 means it is 5 into 4 by 2, which is 10 edges. We have 10 edges here. 1, 2. I will just denote it by Roman letter. 1, 2. This is 3. This is 4. This is 5th edge. This is 6th edge. This is 7th edge. This is our 8th edge. This is this one. This is our 9th edge. And this one is our 10th edge. So we have 10 edges in that accordingly. Then regular graph, if each vertex of a graph has the same number of neighbors, means every vertex will have the same degree. It is known as a regular graph. Means every vertex has the same degree. A regular graph with vertices of degree k is called a k-regular graph or a regular graph of degree k. Let's see some example here. This is a regular graph. We call it as one regular graph. This is a two regular graph, because for every vertex, the degree is, for vertex 2, degree is 1, for vertex 1, degree is 1, for vertex 1 here, degree is 2, and for 2 also it is 2, for 3 also it is 2. So you call it as two regular graph. This one you call it as one regular graph. Then next one, connected and strongly connected graphs. An undirected graph is said to be connected if all pair of vertices, there exists a path between them. So there are 5 vertices. This is an undirected graph because there are no directions specified in the edges. This is a connected graph because for all pairs of vertices, means for example, if I consider 1 to 2, there exists a path between them. 1 to 2, there is a path. Similarly, 1 to 3, there is a path. 1 to 4, there is a path. Even 1 to 5, there is a path. You can go like this, or you can go like this also. So likewise, every vertex will have a path. Every 2 vertices will have a path between them. Now, even 5 and 3 also there is a path. So I can go from 5 to 4, and then 4 to 1, and then 1 to 3. There is a path available. A directed graph, this is a directed graph, is said to be strongly connected if all pair of vertices I comma j, there exists a path from I to j and a path from j to I. Means if I take 1 to 2, it is directly a path is there. If I consider 1 to 4, there is a path 1, 2, and then 4. Even reverse, 4 to 1, is there a path? Yes, it is there. Let me consider 1 to 5. Is there a path? Yes, 1 to 2, 2 to 4, 4 to 5. What about 5 to 1, 5 to 4, and then 4 to 1? There is a path available. So we call this particular diagram as a strongly connected graph. Then disconnected graph. See, if I consider this together as one single graph, there is no path from 1 to 3 or 1 to 4 or 2 to 3 or 2 to 4 or the otherwise, means 4 to 1 or 4 to 2, there is no path, or 3 to 2, 4 to 2, there is no path. A graph in which there do not exist any path between at least one pair of vertices is called as a disconnected. That is why we call this as a disconnected graph. Next, weighted graphs. A weighted graph, whether it is undirected or directed, capital G, consists of a set of vertices V, a set of edges which we call it as capital E, and weights are assigned to every edge. If every edge in a graph is assigned a value or weight or cost that may represent the traveling cost from, say, vertex I to vertex J, the weight may represent the distance traveled or fuel consumed, etc. It can be anything which we are interested in minimizing it. Such type of variables may be possible. It can be distance, or it can be fuel consumed, or it can be anything related to cost, etc. If the weights are not assigned to the edges, then it is called as a non-weighted graph. So that is what it is. So whether you assign some numbers as weights, then you call it as a weighted graph. Otherwise, it is a non-weighted graph. Till now, whatever we had seen are all non-weighted graphs. Subsequently, we'll be seeing some specific examples for weighted graphs also, where there will be some numbers on the edges specified, which we call it as weights. Next one, cycle graph, a simple graph of n vertices where n is greater than or equal to 3 and n edges forming a cycle of length n is called a cycle graph. In a cycle graph, all the vertices will have degree 2. See, if we take into consideration V1, it has got a degree 2 because it is connected with V2 and connected with P3. Likewise, each of the vertices will have degree 2 only. This graph is denoted by C suffix n, where n is the number of vertices in that graph. So this is a cycle 3 graph, this is a cycle 4 graph, this is a cycle 5 graph. So in each of these graphs, you may notice each vertex will have degree 2 only. Then comes wheel. We obtain a wheel when we add an additional vertex to a cycle. For example, in this, in between, we put a vertex and then we are connecting it and connect this new vertex to each of the n vertices. So after I put that vertex V4, I'm connecting V4 with each of the vertex. Similarly, if I put V5 here, I'm connecting this V5 to each of the vertex like this. Similarly, here V6 I incorporated, then I'm supposed to connect with each. Here also it has to connect. Everything we are connecting with each of the vertex by new edges. So these are the new edges, whatever we connected. Each center part has got the new. This we call it as a wheel. Then acyclic graph. A graph not containing any cycle in it is called an acyclic graph. So definitely this is not forming any cycle, so it is definitely a acyclic graph. Finite graph, a graph consisting of finite number of vertices and edges is called as a finite graph. Till now, whatever graphs we saw, all are finite graphs. Whereas this example, if you look into, it's an infinite graph. Why? Graph consisting of infinite number of vertices and edges is called as an infinite graph because it is not closed anywhere. It is going, keep on going. Here also it is keep on going, keep on going, keep on going, keep on going, keep on going. We don't know what it is, but it may have some vertices and edges. Indefinitely, we don't know how much it is. That is why it is called as an infinite graph. Then comes planar graph. It is a graph that we can draw in a plane such that no two edges of it cross each other. These two are examples of planar graph because you don't find any edge crossing another edge. For example, if you look into the second graph, 1 to 3, if I put this here like this in between, which will cut this 4 to 2 edge, then you can't call it as a planar graph. That is why here we are connecting 1 to 3 like this. So that is why it is a planar graph. Then comes bipartite graph. It is a graph where vertices can be divided into two sets, let us say X and Y. The vertices of set X only join with the vertices of set Y. This we are actually considering it as X. This we are considering it as Y. None of the vertices belonging to the same set join each other. Means all these vertices, there is no connection between these four vertices. There is no connection between these three vertices among themselves. Whereas there is a connection from this set to this set. Like for example, 1 to 6, there is a connection. 2 to 6, there is a connection. 3 to 5, there is a connection. 3 to 7, 4 to 7. So from this set to this set, there is a connection. Within this, there is no connection. Within this, there is no connection. So none of the vertices belonging to the same set join each other. Example, vertices 1, 2, 3, 4, 5, vertex set, which is 1, 2, 3, 4, 5, 6, 7, this one together. Then vertex 1 set, we are considering this 1, 2, 3, 4. Vertex 2 set, we are considering these 2, 4. So basically, instead of writing X, I can also write it as V1 because that is what we have written here. This is V2. So here, in general, it is X and Y. Specifically for this example, it is V1 and V2. That is bipartite graph. So in further videos, we'll understand about some more types of graphs. So in case if you find the contents of this video to be useful to you, I request you to please like it, share it with your friends, and also subscribe to my channel. Thank you.